Muy buenos días a todos. La Academia Mexicana de Óptica, AMO, y el comité organizador del Mexican Optical and Society and Photonics Meeting, MOPM 2021, les da la más cordial bienvenida a este evento. We welcome our colleagues from all over the world. Yo soy María del Rayo Aparicio, secretaria de la AMO y miembro del comité organizador de este evento. Es un gusto tenerlos aquí reunidos para compartir conocimientos y experiencias. El día de hoy iniciamos los trabajos de la edición 2021 de la MOP con un gran entusiasmo y con la certidumbre de que esta reunión resultará provechosa para todos los que en ella participan. To begin, I'm very pleased to introduce the Presidium members. Para iniciar, me es muy grato presentar a los miembros del Presidium, en su mayoría miembros del comité organizador de la MOP 2021. Doctora Rosario Porras Aguilar, investigadora de la Universidad de Carolina del Norte en Charlotte. Doctor Guillermo García Tolares, profesor de la Universidad de Guadalajara. Doctor Miguel Torres Cisneros, profesor titular de la Universidad de Guanajuato. Doctora Diana Tentoy Santa Cruz, investigadora titular del CICESE en Baja California. Doctor Roberto Machorro Mejía, investigador titular del Centro de Nanociencias y Nanotecnología de la UNAM. Doctor Víctor Coello Cárdenas, titular del CICESE, Unidad Monterrey y vicepresidente de la AMO. Doctor Eduardo Tepichín, investigador del Instituto Nacional de Astrofísica, Óptica y Electrónica, presidente de la AMO. Profesor James K. Wyant, miembro profesor del College of Optical Sciences de la Universidad de Arizona. Y el doctor Daniel Malacar Hernández, investigador emérito del CIO. I give the floor to Dr. Víctor Coello. A continuación, cedo el uso de la palabra al doctor Víctor Coello Cárdenas.
Thank you very much, María del Rayo. Welcome all to this event. I'm very happy to be here, of course, and very excited to hear of the talks and everything that is coming in the next 3 days long of this conference. The Mexican Optics and Photonics Meeting is organized every 2 years by the Academia Mexicana of Optics, or the Optica, and also by the Mexican Mexico, which is part of the Mexico Territorial Committee for Optics of the International Commission of Optic ICO. Of course, it have been difficult times. We all know what is going on around the world, but this is a time for United to hear the really latest result in optics in Mexico and, of course, of the colleagues all over the world. And then we are thinking to put a special focus on young minds. In fact, the first talk will be an inspiration for them, what is going to happen or why to study this kind of research. And we will have also talks and posters in topics such as laser processing, fabrication of photonics devices, fabrication of nanostructures, which is a very hot topics in the world. We will also see tomography applications in optics in non-degenerative inheritance, which is, of course, very nowadays of importance, and novel measurement of focal distance. Furthermore, we are going to hear in another block nonlinear nanophotonics. Nonlinear nanophotonics, which is a very excited field in the nanophotonic world. I think it's one of the most unexplored things about nano, and then it's going to happen tomorrow. Also, we are going to hear in that block applications of optical vision, and then we will have an extra block about the entrepreneur of photonics. I think this is for the most of us really exciting field, how to put the money into our applications. Also, it will be connected with optical brain interface, and then also a provocative talk about a conspiration in quantum quit information. Don't miss it. Finally, also we are going to review blood glucose concentration, reconfigurable microscopy, and then a very nice advice for students in optics for Professor Joseph Goodman. and How Light Behaves When the Refracted Index Vanishes, also by Professor Robert Boyd. We also invited you to attend the poster participation, which is mostly driven by young minds. We have around 100 posters in afternoon sessions. So I hope you enjoy this meeting. And then if anything we can do for you as an organizing committee, please do not hesitate to contact us. So thank you very much and enjoy the meeting.
Disculpen, muchas gracias, doctor Coelho. Ahora toca el turno al doctor Eduardo Tepechín Rodríguez, presidente de la AMO.
Gracias, doctora. Bienvenidos a todos, estimados colegas. Dear colleagues, welcome. We are very pleased to have you here. No? As this is an attempt to project what happens in Mexico in optics. No, it's our great pleasure to have here in this audience Professor Daniel Malacara, which without any doubt, he was the founder of the optics in Mexico. No, he was the first optician in Mexico. No, he brings these science to Mexico. Now the field is wide open, and together with all our friends abroad, I hope friends abroad, like for example Professor Jim Wyant, who has helped to develop the optics in Mexico, we have a very wide range of applications, as already Victor Coelho commented. So you are very, very welcome to join us during these 3 days. Remember that this is our first attempt to have this conference in distance, in a virtual fashion, but a synchronic one. So it means that all our conference will be given directly by the speakers and not, hopefully, and not with a recorder. So they will be here to interact with you. Please enjoy the platform because in there's a space where you can chat with your colleagues. The intention is to have this presence experience as much as possible reproduced with our platform. So very welcome and thank you for being with us. Gracias, colegas. Bienvenidos.
Muchas gracias, Dr. Tepechín, por sus palabras. I now give the floor to Professor Wyant.
Okay, well, thank you very much. I have to say that I'm very honored to be invited to give a talk at this Mexican Optics and Photonics meeting, MOPM 2021. And I'm especially honored to be invited to say a few words at this opening ceremony. I have many friends in the Mexican optics and photonics community, and this started for me back in 1966 when I first met Daniel Malacara. I was a first-year graduate student at the University of Rochester, and Daniel had just received his PhD a year or two before that, and he came back to Rochester to visit. And I had the opportunity to have a very good talk with him. And I realized that he and I had a lot of very similar interests. And over the years, we have become very good friends. He has come to see me in the US several times, both when I was working in Boston and at the University of Arizona here in Tucson, Arizona. And I have gone to Lyon to visit Malacara and his institute, given short courses there, talks there, even attended one graduation ceremony and wrote several book chapters for Malacara's famous optical shop testing book. Now, I have visited, over the years, I have visited many optics and photonics institutes in Mexico, and I am impressed with the programs and the people. You really cover a lot of areas of optics and photonics. And the Mexican optics and photonics people are very well known internationally and highly respected throughout the world. And I would like to congratulate you on all the great work you have done in the last several years. And I will close by saying, again, I'm very honored to be part of this meeting. Thank you very much.
Thank you, Professor Wyant. You also have good friends in Mexico. Nuestro siguiente invitado es el doctor Daniel Malacara Hernández, quien entre sus muchas aportaciones al avance de la óptica en México, Fue socio fundador de la AMO y el primer presidente de la misma. Él nos dirigirá unas palabras y hará la inauguración oficial de este evento.
Good morning to everyone. I am very happy to see many friends, if not presently, at least through internet. Today, we are having one more of our Academia Mexicana de Óptica meetings, the 2021 Mexican Optics and Photonics meeting with international participants with a very high scientific prestige. We are grateful to all of them. The Academia Mexicana de Óptica was established 34 years ago in 1987 in León, Guanajuato. This academy placed a special emphasis on quality and prestige of its members by communicating all our scientific ideas between us and planning together activities that help us to increase the number of specialists in optics working or collaborating in Mexico. Here I have to mention that we have had in the past and in the present great support and help in many ways from highly recognized scientists and scientific societies like SPI and Optica, formerly the Optical Society of America, in many parts of the world that have made us easier and more successful our work. One important example is their participation today in this meeting. Today, we will have talks by several well-known researchers. Most of them, no, I'm sorry, not most, all of them, very good friends of mine. I am very happy to see them. I am not going to mention them because you already know all their names, but I welcome all of them and thank them for their help. All of these talks will be quite interesting. Please enjoy them. I have the pleasure to declare inaugurated the works of the 2021 Mexican Academy of Optics meeting. Please enjoy it. Thank you very much.
Muchas gracias, doctor Malacara. Antes de iniciar nuestra primera conferencia plenaria, voy a dar 3 anuncios. En primer lugar, les recordamos que todas las exposiciones de conferencias y presentación de trabajos se llevarán a cabo a través de la plataforma del evento. En segundo lugar, los trabajos marcados con números pares se presentan hoy jueves y los marcados con números impares mañana viernes. Finalmente, les informamos que entre conferencia y conferencia es necesario desconectarse y volver a conectarse 2 minutos antes de iniciar la exposición. Enjoy this event very much. We will be back in 10 minutes. Que disfruten mucho de esta reunión. Regresamos en 10 minutos.
Professor Jimmy, good morning. Can you share your presentation, please?
Okay, I will. Do you see it okay?
Yes, yes, I can see.
Okay, very good.
Thank you.
Mhm.
Eduardo, veo una imagen del Optical Sciences y no tengo nada de audio. ¿Es normal eso ahorita? Pues entré ya. Déjame ver qué debo hacer. A lo mejor no estoy haciendo bien las cosas. Yo nada más veo la imagen estática del edificio y abajo tengo Share Screen. O me voy a participantes, o me voy a chat, o me voy a dónde.
¿Qué tal, doctor? Buenos días. ¿Nos escucha?
Ahorita sí escucho.
Ok, perfectísimo. Ya estamos listos. Ya hicimos pruebas con el doctor Wyant de su presentación, por eso es que ya la ve ahí en su pantalla. Si gusta...
En la pantalla veo nada más el edificio de Arizona.
Ok, presione la tecla de escape para que deje de ver la pantalla completa. Escape.
Escape. Sí.
Listo, ya debe ver más opciones en su pantalla.
Sí. Ahora...
seguirá viendo la pantalla, pero esa es la presentación del doctor Wyant.
Ahora veo, puedo poner a Jim, ¿verdad? Para verlo. Bueno, quiero un cuadrito pequeño.
Sí.
Muy bien. Entonces, ¿aquí ya estamos listos?
Aquí ya estamos listos. En 3 minutos, un poquito menos, comenzamos.
Muy bien.
Antes de comenzar, yo le voy a avisar unos 5 segundos antes. Usted va a hacer una cuenta regresiva mental de 5 segundos y comienza.
Perfecto, gracias.
Gracias.
Good morning to all again. To begin our talks of the 2021 Mexican Academy of Optics meeting, I have the great honor to present our first speaker, my friend for more than half a century, Professor Jim Wyant. He is an extremely well-known scientist and a very good close friend of mine, as I said, for so many years. Jim is a wonderful scientist in many senses. He is probably the best in the world in the field of interferometry and optical testing, and the inventor of many instruments. But he has not only dedicated his time to the academic field, he has also been the founder of several optical companies to commercially produce with great success these instruments. Professor Wyant obtained his master's and PhD degrees in optics at the Institute of Optics, where I met him for the first time at the University of Rochester in 1967 and 1968, respectively. He was the founding dean of the College of Optical Sciences at the University of Arizona. The Institution for Research in Optics at the University of Arizona has its name, James C. Wyant College of Optical Sciences. He has received a large number of awards. If I am to mention all these awards, I will stay the whole conference time talking about him. So I will not mention them because they are very well known, and I am sure he will collect more awards during the rest of his life. So Jim will try to convince young people that of something we already know. It is a wonderful to have a career in optics and photonics. Thank you very much, Jim. You have the word.
Okay, well, thank you very much, Daniel. I'd like to thank you and all the organizers for inviting me to give this presentation on one of my favorite topics, because I do indeed think it's wonderful to have a career in optics and photonics. So I will start out here by saying a little bit about why optics is a very good career to work in, why it can be a lot of fun. And then I'm going to spend time talking about my particular career to give you an idea of how much fun I have had. Maybe at this point I should stop for a second and ask to make sure you see the slides okay and the audio is okay. Is that true? Okay. So, you know, you want to decide what is it I want to do for my career. And when I was a young student, I was really puzzled because I didn't know if I wanted to be a scientist or an engineer. Well, you can be either one. You know, are you interested in medicine? Maybe so, maybe not. Do you enjoy working with electronics? Maybe so, maybe not. Are you interested in computers and software? But if your answer to any one of these questions is yes, then you really should consider a career in optics and photonics, because you can do all these things in optics and photonics. So why optics? Well, optics is involved with everything. It's the technological enabler. It's just involved in all types of things in our lives: healthcare, telecommunications, you know, cameras, displays, measurement, illumination, energy, microelectronics, nanotechnology, and a lot more than that. Optics, you know, we all have a cell phone nowadays. Some of them are iPhones, some are other cell phones. But all of these cell phones, we think of them as being maybe computers, or we think of them as being electronics. But they really are filled with optics. For example, in this cell phone, we have a camera or a couple of cameras. And every camera has a lens, has a detector, so that's optics. The display here is optics too. And, you know, if you're talking to someone over the phone, or if you're communicating with someone over the web, probably that signal is going over fiber optic. And even the chips in this cell phone were made using optics. We would not have a cell phone without all the optics that we now have. And in this particular cell phone I'm showing here, iPhone, it's a face recognition system in it. And that's in this little dark area at the top. And what's actually in here are some 400 lasers illuminating your face to see if they recognize you, see if the phone recognizes you or not. So it's just optics, optics, optics. And if we think about in our daily lives, LED traffic lights, optics, laser traffic radar, all types of motion sensors, optics, photocopiers, the high reflectivity surfaces for highway signs, optics, photolithography, as I said before, laser printers, and so on. So this are just a few examples of optics in our daily lives. And I'm going to show a few more here. Laser surgery. I mean, optics is involved in so many instances in medicine. A lot of the medical tests are optics-based. Microscopes, cameras, barcode scanners, credit card holograms, and optical inspection, laser welding, and so on. And one more slide to emphasize the point that, you know, as you go through your daily life, you just see optics every place here. Oops. All kinds of LEDs, LCDs, optical fibers, infrared automobile security systems, laser fabric cutting, and so on. Just optics is every place. So think about it as you go through a day, look at all the cases where optics are helping you. The other thing I like about optics is that optics it can be beautiful. One of the main reasons I went into optics was I saw all these beautiful things in optics. And I especially like thin film interference with soap bubbles. So 3 or 4 years ago, I decided I would write a short article on thin film interference with soap bubbles. And I figured this article would take me maybe a day or two to write. But I spent 2 or 3 weeks just taking photographs. I was having so much fun photographing these soap bubbles. I have hundreds of photographs of soap bubbles on my computer here. So optics can really be interesting and fun. So there. So, you know, when I was young, I was also thinking, well, do I want to work in industry? Do I want to be a university professor? Do I want to start a company? And my problem was I wanted to do all of these. But the fortunate thing is that I have been able to do all of these. When I first got out of University of Rochester, I worked in industry in the Boston area for about 6 years, worked for a company called iTech that was in a satellite reconnaissance systems business. And I had a lot of fun there doing a lot of different things. And what was really great was the people I was working with were really smart. They really knew the material. And I always said that, you know, I learned more during those 6 years working in industry than I learned in college. It was just a wonderful, wonderful experience. Well, after 6 years, I got an opportunity to join the faculty at the University of Arizona. And I jumped at the chance. I was so excited. I wanted to do that. So I moved to Tucson, Arizona. And I was faculty member for many, many years there. And for the first 10 years, I was a full-time faculty member. But then I got the urge to start a company. And so after about 10 years, I started a company. And I still stayed on 20% time at the university because I love teaching. But I spent most of my time with this company. And what I want to do now is to talk about 2 different companies that I started and kind of show you the excitement and the fun I had with these companies. So this is some of the experiences gained in starting and growing 2 different optical companies. Well, first off, we might say, why did I want to start a company? And if I were there in person, I would ask the audience, how many of you would like to start a company? And I would guess there's quite a few. So why start a company? Well, I really had two reasons for doing it. One was to have fun. And I did have a lot of fun, as I try to show you in the next few minutes. The other reason I started a company was to make money, of course. Sometimes when you start a company, you make money, and sometimes you don't. But fortunately, I was lucky. So if you're going to start a company, you have to have a product to sell. And I really thought for a long time, what product could I sell? It took me maybe 2 years of thinking here before I finally came up with the first product. And it was a product, an automated, by automated I mean computerized interference microscope for measuring the surface quality of optics. And in particular for diamond turned mirrors, because I knew I had someone who wanted to buy one of these instruments to measure the surface roughness of their diamond turned mirror. So thought for a while, and it ended up 4 of us went together to start this company. One was a postdoc of mine, one was a research associate of mine, one was a former student of mine who had just received his PhD, and then myself. So after thinking and working for a while, we finally came up with this, which is just a basic microscope, illuminator here, light goes down to the objective. This was an interference microscope. So we had put some interferometer down here between the objective and the sample. And for this particular case, we used what's called a Moreau interferometer. Get this, we measure I of xy, we claim we know phi of t, we don't know I sub dc or I sub ac or phi of xy. So we have 3 unknowns, we need some way we need to get 3 equations to solve for these unknowns. And so if you first say let phi of t be 0, you get this equation here with a cosine. If I now move the reference surface, so the phase difference changes by 90 degrees. That plus cosine becomes a minus sine. I move the reference surface again. And so another 90 degree phase shift. That minus sine becomes a minus cosine. So I have 3 equations and 3 unknowns. And I could use this to solve for phi of xy. But typically we would use 4 steps instead of 3. And I won't go into the details of why we did that. But good reasons for it. And so now we just take the difference between I4 and I2 and divide that by the difference between I1 and I4. And you end up with a sine over the cosine or the tangent of phi. And then you solve for phi. And you can do this for points across the surface, and you'll determine the height variations across the surface very accurately. And just again, back to the diagram that I had before. Now, this is very simple in principle. It was harder than that to actually make it work. This is our first, well, almost the first microscope. I have this, still have this one at home in my garage. It took us, this is what I call a pre-prototype. And it really took us about 2 years to come up with the real product that we were selling. And we call that Topo 3D. And this worked very well. You could measure diamond turn surfaces. So this is looking at a profile of a diamond turn surface. So this height would be nanometers. The distance along here would be microns. You could also do a three-dimensional plot of the surface heights. So it worked very well for diamond turn surfaces, but it also worked very well for all different types of smooth surfaces. I mean, this was a great instrument, and we sold more than 1,000 of these Topo 3Ds. So it was very good for smooth surfaces, but we had people who wanted to measure rougher surfaces. So how can you do that? Well, we went back to very basic optics, white light interference fringes. And you know that if you use a broad bandwidth, white light, you're going to get good contrast fringes only when the paths of the two arms of the interferometer are matched. And as you get a path difference between the two arms of the interferometer, the fringes for the different wavelengths get out of step, and the contrast drops off. So we wanted to use this as a way to measure rough surfaces, namely that the fringe contrast would be greatest at the point of equal path length, or best focus in our microscope system. So we basically went to the same interferometer, same microscope we had before. We took out the filter, so we had white light. The translator here was, which before just moved fractions of wavelengths to get the phase shift. Now it was replaced with a translator that would also move microns. And so the idea here is that if you have your microscope set up and say this is a spherical surface you're measuring, if the paths are matched right where this red line is, right at the top of this curved surface, you're going to get the best contrast fringes in the center. As you move the microscope projecting the reference surface down, now the paths are matched down here. So the position of best contrast fringes will move out. If you move it down more, they would move out even more. So the idea is you do a vertical scan, and you keep track of where the fringes are best, what the position of the microscope objective is for the best contrast fringes for point by point along the surface. And that way you can map out the shape of the surface of even a rough surface. And this is the instrument that we built for that, very similar to the previous instrument, but a little more sophisticated, I would say. And here's measuring a step height. This is about 48 microns high. So as you would move the microscope, as a computer would move the microscope objective through in a vertical direction, you would first get good contrast fringes on the high spot. Then later you get good contrast fringes on the lower spot, and the distance the objective moved between good contrast fringes here and good contrast fringes down here tells you what the height was, about 48 microns. This was used to measure lots of surfaces. Give a couple of examples here. This is a print roller that has a lot of pits in it for holding ink. Now it doesn't look like something you would test with an interferometer, but it actually worked very well with this interferometer. And we were able to measure the pits, how high they were, point by point across the sample. We could look at machine parts, measure the roughness of machine parts, even look at cloth, measure what the surface looked like on the cloth. And the real product that the real business turned out to be magnetic recording heads. So we came out with this instrument just about the time that computers with hard disk drives in them became popular. Everyone wanted a hard disk drive. The people who made the hard disk drives had a lot of trouble of making these recording heads. And so each drive would have 1, 2, 4, 6 or more recording heads. And every single recording head had to be measured. They were having so much trouble manufacturing them, they had to measure every single one to make sure that it had the right shape. And it turned out, by luck, I have to admit, our instrument did that extremely well. And we sold thousands of these instruments. Essentially, everyone in the world who was making hard disk drives, making the heads for hard disk drives, had to buy instruments from us to measure every single head they made. This was really a lot of fun. Well, we built a lot of different products at Wyant. Some of them were very successful. One in particular was very unsuccessful. And of course, that's the one I want to talk about, the unsuccessful one. I tell you, it was so much fun, even though it was not a great success. So this goes back to maybe what some of you know. If you project lines or fringes onto a surface, and say they have a spacing of d, and you project them on an angle of alpha, then you view where these lines illuminate the surface at some angle beta, what you see is something that's very much like an interference pattern, except now the wavelength used for measuring is not the wavelength of the light, but it's what I'll call an equivalent wavelength given by 2D divided by tangent alpha and beta. So by varying D and alpha and beta, you can vary the sensitivity. So we basically took our similar technology we were using before. We set up an interferometer, produced interference fringes, and we could vary the spacing of these fringes. And then we would view the fringes down here, and we could shift the fringes just like we're doing in phase shifting interferometry, and we could measure then the shape of this surface, and we could vary the sensitivity by varying the spacing of these fringes and the angles that we're illuminating and viewing from. So one thing you could measure would be the shape of tin cans. Well, I hate to say it, I never found anyone who wanted to buy one of these instruments for measuring tin cans. Well, you could measure the shape of your hand if you wanted to. I thought people would want that for people making gloves or something. No one wanted to buy that. So here we had a great instrument, but we had no customers. Well, one day, this guy walked in to our place and said he wanted to measure something. But he was a very secretive guy, and he wouldn't tell us what he wanted to measure. So I thought, how do we do anything for him? So I decided I'd give him a little tour, take him to the front door and say goodbye. Well, we got in the room where we had this equipment set up, and he got all excited. He took his shoe off, he took his sock off, and he held his foot up. It was just the laser beam used in the system was just the right height for where he could raise his foot up to. He said, measure the shape of the bottom of the foot. I pressed the button on the computer and actually measured the shape of the bottom of his foot. And he was so excited because this is what he wanted to measure. He was a podiatrist, foot doctor, and he sold a lot of orthotics. And to determine the shape of the orthotic, he would use a plaster cast. And he thought a technique like this would be much better for measuring the shape of the foot. So we went into a little business together to make foot scanners. And so we built this foot scanner, and it worked very well. I was so impressed how well it worked. But then we ran into our fundamental problem. We were used to making instruments that we would sell for $100,000 or $200,000. And these podiatrists didn't want anything that expensive. So we worked, and we brought the cost of this down so we could sell it for about $12,500 and make money. But that still wasn't low enough. The podiatrists would only pay about $2,500 for an instrument like that. And we just were not able to bring the price down where we could sell it for that price. So I think, well, we spent a lot of money developing this instrument. We sold only 4 of the instruments. They worked well, but no one wanted to pay the amount of money they cost. But I do still have 2 of these instruments home in my garage. You know, if anyone wants to buy one, I can give you a special deal. Anyway, it was a lot of fun. Didn't make money, lost money on this, but it really was a lot of fun. Well, after doing this company for about 13 years, I really got the urge to go back to the university full-time. I had stayed part-time, but I wanted to go back full-time. And thinking back, you know, and I did. So we sold the company and I went back to the university full-time. So to think back on the company and what was most important, well, you have to have a product that people want to buy. You have to be willing to do whatever it takes to get the job done. Oops. You have to be good at hiring people. That is so important, and especially very important. Well, you have to have good timing, like we had with the magnetic recording heads, and you have to be lucky. So these are kind of the most important things. Well, anyway, I went back to university and I put together a research group. But in about a year, I had the chance to become the head of what was then called the Optical Sciences Center. So I jumped at that and took that. And then we were able to grow the center, so it became a college, and I became the dean of the college. So I was having a lot of fun back at the university. But you know what? Doing companies is a disease. Once you do one, you want to do another one. And so we started another company called 4D Technology. Now, the product here, it was somewhat similar to what we had before at Wyco, but a problem we always had at Wyco with our instruments was vibration. We were taking 4 frames of data at different times, and any vibration in the system would just mess up the phase difference between these 4 frames. And so it was a serious problem. We always used vibration isolated tables and did everything we could to get rid of vibrations, but it was a problem. So I decided at that point I really wanted to solve this vibration problem. So we went to work. We came up with several ideas, but one idea was far better than the rest, and that's what the company was based on. And that was based upon a very old idea. And you know, I have found over the years that if you want to do something new, sometimes it works very well to pick an old idea and apply new technology to that idea. So that's what we did here. I'll describe it very briefly. It's well known that they have 2 beams that are coherent with respect to each other, but one is made right-handed circular and the other one is left-handed circular. These 2 beams will not interfere because they have orthogonal polarization. But if you send these 2 beams through a polarizer, you will see interference fringes. And the interesting thing is that the phase of these interference fringes depends upon the orientation of this linear polarizer. And if I rotate this an angle alpha, the phase will be changed by 2 alpha, independent of wavelength. It's really useful, but it's been known a long time. But the new thing that we're bringing to the party was using modern lithography tools, you could make very small polarizer by drawing a bunch of lines. And you could make these so that they were the size of a detector element. And we could sort of make this up of groups of 4, where if each group would have 4 polarizers that would vary by 45 degrees. And so The interference of the light going through here would vary by 90 degrees and going from one to the next. And so we would have our 4 phase shifted frames, but we would have them all at once. And vibration wouldn't bother us nearly as much. And so the idea is to build an interferometer where the reference beam and the test beam one has right-handed circular polarization and the other one is left-handed circular. You take this little pixelated mask that you made using lithography techniques, and that's made up of a bunch of groups of what I call A, B, C, and D, A, B, C, and D. And you put that right in front of the detector and you align it with the detector, which turns out to be easier than you think it might be. And if I take all the A's, I'll get this interferogram. All the B's, I get this. C's, D's, and so I have my 4 phase shifted interferograms all at once. And setting up here, I could have a mirror and an interferometer on separate tables. I could have vibration, no vibration isolation, and I still could get very good contrast interference. If I had a surface that was changing shape with time, you could also, you could make a video of how the shape changed with time. And this just worked so well, and it opened up so many opportunities for using interferometers where you couldn't use them before. Well, about this time, the people doing the James Webb Space Telescope came to us and said they had a lot of metrology problems and they wanted to know if we could help them. And of course I said, yes. So this is the James Webb Space Telescope. I'll say a little bit more about it in just a minute. But here's the mirror, primary mirror, secondary mirror, and this is a sun shield down here. So this primary mirror is made up of 18 hexagonal segments. And the collecting area of this is about 6.25 times the collecting area of the Hubble primary mirror. So the types of measurements they wanted was they wanted to measure the shape of the primary mirror. There's a back structure holding these segments together, and they needed to know how the shape of that back structure would change as the temperature changed or as the mechanical load changed. They had to phase these segments, they had problems with thermomechanical strain, had problems with vibrations. And so we used this technology to build the instruments to do these various measurements. We could do an end-to-end test of the telescope. We could test the secondary mirror. We could test just the primary mirror by itself. We could do these tests at room temperature or at very low temperatures. There was problems with edge roll off here, and we were able to measure that shape of that, so that could be corrected. We were able to phase the mirror. There were other sensors that will be used in space to phase the mirror, but we were able to calibrate these sensors using our equipment. And this back structure is this dark area here. We were able to measure that to see not the shape of it so much, but to see how the shape changed as the temperature or the mechanical load changed. And we were able to do a test of the primary mirror here. So this is the mirror, and over here is an interferometer. No vibration isolation or anything. Even if you have air turbulence, you just take a lot of measurements and you can average out the effect of air turbulence. So it sort of changed the way the optical testing is being done, being able to do these single shot measurements. And there are other ways to do it besides what we did here, but our way certainly worked very well. So I'll just mention that this James Webb Space Telescope is now scheduled to be launched on December 18th of this year. So we all have our fingers crossed that the launch works okay. So in conclusion here, you know what? A career in optics and photonics can be a lot of fun. And I think you can find that it's fun whether you work in industry, you work in university, you do your own company or whatever. You can find all kinds of things that are really a lot of fun. And with that, I will say thank you very much. Thank you.
Jim, thank you very much for this wonderful talk. You have really enjoyed life. I'm very happy with this.
Well, you've enjoyed life too.
Thank you. Well, I have a few questions.
Oh, no.
The first one is by Maria. It's really not a question, it's a comment with which I agree. I fully agree. She says, I studied optics, but your conference convinced me. So in my second life, I will study optics again. I say it's exactly the same thing. Optics is wonderful. We play like children. Do you agree?
I agree. I mean, I would do optics again because you get into so many different areas. And if it's, you know, computers you like, you do that, or medicine, or whatever. And optics is involved. And it's just a very enjoyable career.
Yes. The second question by Eduardo is phase step interferometry an on-axis procedure in the microscope?
Can you repeat that? I didn't quite get it. In the microscope, what's this?
In the phase step interferometry, is this an on-axis procedure in the microscope?
Yeah, well, in the one that we built, it was on-axis. We used different types of interference objectives. The Moreau I showed you, a Michelson type or a Linux type, but they're all on-axis.
Well, a second question also by Eduardo is, how can you measure or calculate the resolution in the phase step technology? What happens with the focus when projecting the fringes?
Well, again, I have to ask you.
I understand. How do you calculate the question like this? How do you calculate the resolution in the phase? What is the accuracy that you have?
Okay, so the repeatability is for the smooth system could be better than an angstrom. Now to get that, so the height repeatability, I'm not saying accuracy, but the height repeatability is less than an angstrom, can be, and you achieve that a lot by averaging, because you can average several frames. And we did a lot of work with height standards from NIST, and we compared our measurements with STM and AFM measurements. And so we knew the repeatability very well. The accuracy we knew not quite that well, but certainly in the nanometer range.
Okay. I have two more questions, one by Maria and one by Eduardo, and they are close related.
Okay.
So I'm going to tell you the two questions. The first one is, how related are universities and industries in your country? And the other question is, how long did it take for you to sell your first product? What about funding?
Okay, so the universities and companies have much more closely worked together now than what they did, say, when I started the career. And we do a lot of work at the university. We do a lot of projects for universities. And so it's pretty closely related. We also do a lot of patents that we license to companies. So the university works pretty closely with with companies. I've forgotten, what was the second part of the question?
The second part of the question is, how long did it take to sell your first product?
Well, I didn't tell the whole story here. I first had a company making software, called it Wyant Measurement Systems, and software for analyzing interferograms. And so that got some money to start the company and to buy some of the first computers and whatever. And then we worked very closely with IBM, and they bought a system from us that actually took us 2 years to deliver, but they paid us 60% of the money up front. And even though it took much longer to deliver than what they thought, they didn't really complain. They were very nice to us. And so for the first, I don't know, 10, maybe 20 systems, we gave people a discount if they would pay 60% up front. And that's what we used. We did not take any outside funding from anyone else. And so we probably could have grown faster if we had done that, but it worked out well as it was. And bootstrapping our way up.
I have one last question, or it's really a proposal. Maybe a food scanner should be proposed for a diabetic foot or other medical applications.
I think it could be. And, you know, we stopped working on it because we just couldn't get the price down to where they wanted to buy it. But other people have extended that now, and foot scanners similar to what I showed you are now being sold and used for, you know, various medical applications. It's a nice, and I think you probably have played with the same technology. It's a nice technology because you can vary the sensitivity a lot depending on what you want. And it's fairly simple to do.
Jim, I think we have no more questions, but
okay.
I want to tell you that I was extremely happy today to see you, to hear.
Well, I'm happy to see you. I had not seen you for a while.
Yes.
I used to see you all the time, but COVID came along. I have not seen you for a while. I hope to see you in person before too long.
I hope so too. Thank you very much.
Thank you.